As of now, I defined a new scale in honor of this object that is called the Loeb scale after my last name, with 0 meaning it's a natural object like a comet for sure, and 10 meaning it's definitely a technological object because in case we, for example, see a
Scientists revealed the clearest shot of 3I/Atlas, and NASA is trying to remove it from the internet. But here's what they don't want you to understand. The clearest image we have is a blur. There are images that show us beauty. There are images that show us truth. This one does neither. At first glance, it looks like a failure, a photograph that refused to focus, a technical error uploaded by mistake. But behind that blur is something extraordinary. Motion captured at the edge of physics. Light collected from a traveler that has never belonged to our sun. Something is moving through our solar system right now, and it's breaking every assumption we have about what interstellar visitors should look like. Introduction. Welcome to the story of 3I/Atlas, the third interstellar object ever observed from Earth, currently racing through our solar system at speeds that make conventional photography impossible. When astronomers first detected this visitor from beyond our stellar neighborhood, they knew they had minutes, maybe hours to capture it before it vanished back into the cosmic dark. What they didn't know was that the image they would produce would challenge everything we thought we understood about interstellar objects. This isn't like photographing Mars or Jupiter. Those worlds sit relatively still in our telescopes, patient subjects for our cameras. 3I/Atlas moves too fast and shines too faintly for any normal exposure to work. By the time a telescope collects even a few seconds of light, the object has already traveled thousands of kilometers through space. A single frame would show nothing but a soft streak, a comet-shaped guess stretched by its own motion into meaninglessness. The technical challenge was unprecedented, and the solution? Even more so. To capture 3I/Atlas, astronomers had to do something remarkable. They had to chase it. Imagine trying to photograph a bullet in flight, not from the side, but while running alongside it at the exact same speed. That's essentially what happened here. Tracking software predicted the comet's path second by second, adjusting the telescope mount in near real time. The stars in the background blurred into trails as the telescope pivoted and swept across the sky. But 3I/Atlas held its position. What looks like a still blur in the final image is actually motion perfectly canceled out, a precise balance between the comet's speed and the telescope's pursuit. It's time made visible. Every pixel carries minutes of motion, compressed and rebalanced until stillness could exist where it shouldn't. But even then, one exposure wasn't enough. At magnitude 17, the comet is barely visible to the sensor. For context, that's roughly 25,000 times fainter than what the human eye can detect under perfect conditions. So astronomers stacked multiple long exposures, aligning them until the faintest signal added up to something coherent. Atmospheric tremors had to be filtered away. Instrument vibrations, even temperature changes in the telescope itself, all introduced noise that had to be mathematically removed. The shape that remained was fragile but consistent. A faint cylinder of light that moved faster than our focus, yet slow enough to be caught. What we're looking at isn't just a photo. It's patience transformed into data. Technology and determination bending together to meet something the universe never meant to be seen clearly. 3I/Atlas didn't stop for us. We simply learned how to move with it. In the image, 3I/Atlas doesn't show a surface. There's no crisp edge, no nucleus shining at the center like we'd expect from a typical comet. What we see instead is an outline that refuses to stay defined, a gray body that fades into itself, smooth at one end, uneven at the other. The elongation is unmistakable. It's not round, and it's not random. It holds a structure that almost looks deliberate, but too faint to confirm with certainty. That shape has puzzled everyone studying it. If this were an ordinary comet from our solar system, we'd expect a rounded head and a tail tapering behind it, a classic teardrop pattern shaped by solar wind and radiation pressure. But this isn't that. The frame shows a body that seems evenly stretched, almost like a cylinder without a clear tail direction. The brightness peaks slightly toward one side, which suggests a rotation axis angled toward the observer. If that's correct, the comet could be spinning rapidly enough to blur its features in the exposure, the way a long camera shutter smooths moving water into a flat, glassy surface. But there's something else, something that makes this image even stranger: the color, or rather, the absence of it. When astronomers processed the raw data channels, they found something curious: no real color. Most comets, even faint ones, show at least a hint of tone: a greenish halo from cyanogen gas, a yellow-white tail from reflected sunlight. But 3I/Atlas gives almost nothing. Across visible wavelengths, its spectrum flattens into neutral gray, a silence in color that says more than a bright signal ever could. This absence tells us the object isn't actively outgassing in any strong way. The numbers confirm this. The apparent albedo sits at an estimated 2 to 3%, darker than asphalt, darker than coal. Only the faintest scatter escapes into the visible range, smoothed by interstellar dust that coats the surface. Over millions of years, drifting between stars, that dust has been bombarded by cosmic rays, baking carbon molecules into complex organics. These tholins tint the surface in deep reds at microscopic scale, but when seen from a distance, they combine into neutral gray. The color cancels itself out. This is the color of endurance, of a surface that has traveled for eons without renewal. 3I/Atlas doesn't display color because it no longer needs to. What remains is the faint equilibrium between sunlight and memory. Light reflected off something too ancient to shine. Every faint comet challenges the edge of what our detectors can prove. 3I/Atlas lives right on that border. In its raw data, the comet is barely a presence at all, a whisper above background noise. When you zoom in close enough, even the sky seems louder than the signal. But the difference between random static and a real object comes down to consistency. Real light behaves with intent. It repeats, it aligns, it holds pattern where chaos can't. That's what makes 3I/Atlas image meaningful. Across exposures, the faint streak appears in the exact same coordinates. Its brightness curve remains stable despite atmospheric shifts and thermal noise. That repeatability is the only reason astronomers can call it real. But here's where things get strange. Once the image was assembled, it didn't behave like anything the calibration software was designed for. The algorithms that measure coma curvature, nucleus brightness, and tail direction couldn't settle on a pattern. The numbers diverged depending on which model was applied, each insisting on a different shape. In data terms, that kind of disagreement usually means one of two things: the target is unstable, or the physics behind it doesn't fit existing templates. Most comets follow predictable equations. Solar heat drives sublimation. Jets of gas push outward. Dust streams along the sun's vector to form a tail. But 3I/Atlas breaks that logic. The faint elongation in its image doesn't align with the solar direction at all. It tilts several degrees off, suggesting the body isn't venting material uniformly. It could be rotating rapidly, or shedding particles from a fracture rather than an active jet. Either way, its symmetry refuses to match the models built for local comets. Some analysts compared the brightness pattern to 2I Borisov, the last confirmed interstellar comet. Borisov displayed a textbook coma and tail even when it was still far from the Sun. 3I Atlas, by contrast, behaves more like 1I Oumuamua, an object with no visible coma, only reflected light. Its blur lies between the two, too diffuse to be a solid asteroid, too clean to be an active comet. That ambiguity makes classification nearly impossible. Spectral measurements reinforce the confusion. No strong emission lines appear, no water, no cyanide, no carbon monoxide flares. The spectrum is flat except for a faint dip in the near-infrared, possibly from carbon dioxide ice sublimating under minimal heat. It's as if the object is waking slowly, testing how much sunlight it can absorb before losing structure. When an image can't explain itself, mathematics takes over. The frame of 3I Atlas is too faint, too ambiguous for traditional analysis. So scientists turn to numbers to extract what the light couldn't say directly. Every pixel in the photograph becomes a coordinate, every shade of gray a probability. It's less about seeing the comet and more about understanding how the light must behave for the image to exist at all. The first step is motion modeling. By plotting its position across consecutive nights, astronomers determine its angular velocity, a precise measure of how much sky it crosses over time. That rate, combined with the object's distance from the Sun, translates into a real velocity of roughly 12 kilometers per second, confirming its hyperbolic trajectory. It's moving fast enough that no gravity in the solar system will ever pull it back. Every calculation reinforces what the blur already implied. 3I Atlas is just passing through. Next comes brightness fitting. The faint gradient along its length is modeled to estimate orientation and reflectivity. Simulations show that if the nucleus is elongated, perhaps several times longer than it is wide, then a slow tumble could recreate the uneven brightness we see. The rotation would cause one side to catch sunlight more efficiently before fading again, producing the soft oscillation embedded within the blur. That variation is tiny, almost invisible, but the math detects it where the eye can't. Even the blur itself becomes measurable. By deconvolving the image, reversing the distortions caused by optics and atmosphere, researchers calculate how much of the elongation comes from motion versus shape. The result shows that while tracking smoothed the comet's movement, residual drift still contributed to its stretched appearance. In other words, the blur is part real, part consequence of chasing something that can't quite be caught. At some point, the discussion around 3I Atlas stopped being about what it looked like and became about what it refused to be. Every attempt to classify it pushed against the limits of existing categories. It wasn't a traditional comet, lacking both tail and coma. It wasn't an asteroid either, since its light curve varied too smoothly to come from a rocky surface. The image presented something in between, a blur that resisted interpretation, an object defined by the fact that no model could describe it cleanly. The data now paints a picture of contradiction. The brightness curve remains stable enough to suggest a single body, yet the slight asymmetry hints at motion within motion, perhaps a slow tumble, perhaps fragments orbiting a shared center. Its trajectory confirms an interstellar origin, a hyperbolic path that ensures it will never return. That certainty of escape is, paradoxically, the only thing about it that feels familiar. Astronomers have seen ambiguity before. 1I Oumuamua was too sharp and fast. 2I Borisov was almost too typical. 3I Atlas sits between them, as if bridging the gap. Neither solid rock nor classic comet, neither silent nor active. It behaves like a memory of both. Its faint cylinder of light is the signature of something that exists just beyond the boundaries of resolution and taxonomy. A reminder that our categories are only conveniences, not truth. Even the image itself seems to echo that duality. The blur is both evidence and absence, a confirmed detection that withholds its identity. It forces astronomy to confront the uncomfortable idea that seeing isn't the same as knowing. For centuries, telescopes have given us sharper, deeper views of the cosmos. But objects like 3I Atlas revealed the limits of that progress. Sometimes the clearest image possible is one that refuses to resolve. So the blur remains, not as a flaw, but as a fact. The object escapes our definitions not by hiding, but by existing in the thin space between them, where physics still operates, but language begins to fail. When the light from 3I Atlas finally fades from our sensors, the photograph will remain, a faint smear in the archive, a record of something that passed too quickly to ever be seen clearly. In most branches of science, such an image might be dismissed for lack of detail. In astronomy, it becomes the most honest kind of evidence. A blur is what happens when the scale of the universe meets the limits of our focus. Everything measurable about 3I Atlas exists inside that faint streak. Its velocity, its trajectory, its brightness curve, its distance. From that single unresolved shape, entire models emerge. How it spins, how sunlight touches its surface, what minerals might make it reflect the way it does. The image's weakness is its strength. It forces meaning to come from physics rather than appearance. We don't know what the comet looks like, but we know what it is doing and where it is going. Soon, it will leave our system entirely, receding into the same dark it came from. No future telescope will see it again. Its orbit is unbound, its direction set. The blur we have now is not the beginning of study, but the end of accessibility. The one clear intersection between human observation and an object that belongs to interstellar space. That is what makes this image different from any other comet portrait. It's not a picture of a destination, it's a snapshot of passage. A body formed under another star has crossed through our solar system, leaving nothing behind but the proof that it was here. The photograph doesn't try to beautify it or even define it. It simply shows light doing what light always does, traveling until it's caught, then disappearing into memory. In the end, that's all the evidence astronomy ever holds. Traces of things already gone. 3I Atlas was never truly seen. It was measured by its blur. And that, perhaps, is the clearest image we could ever hope for. A visitor from beyond our sun, caught for one brief moment between arrival and departure. Between visibility and darkness. Between what we can photograph and what we can understand. The clearest shot we have is a blur. And maybe that's exactly what the truth looks like when it moves faster than our ability to focus. Maybe that's what all interstellar visitors will look like. Ghosts in our instruments, whispers in our data. Present long enough to be measured, but never long enough to be known. 3I Atlas is already gone, but the blur remains, a reminder that the universe doesn't owe us clarity, only evidence. And sometimes that evidence arrives in the form of a photograph that refuses to resolve. A cosmic mystery preserved not in sharpness, but in motion. Not in detail, but in departure. That's the image NASA can't remove from the internet. Not because it's too revealing, but because it reveals too little. And in that absence lives the most profound truth of all. We are watching the universe pass by, frame by frame, blur by blur, one interstellar visitor at a time. That's it for today. 3i Atlas continues its journey into the void, never to return. But the questions it leaves behind remain unanswered. What else is out there moving through our solar system undetected? What will the next interstellar visitor reveal? Let us know your thoughts in the comments down below. And if you want to stay ahead of the next cosmic mystery before it disappears into the dark, hit that subscribe button and turn on notifications. Because in space, some discoveries only pass by once. Don't miss the next one.